Dear classmates, welcome back to Combinational ATPG. In the following video, we will introduce many deterministic test pattern generation techniques. These techniques are sorted according to the time they were invented. These techniques can be roughly divided into Boolean-based techniques and the path-based techniques. The Boolean Difference technique and the satisfiability technique belong to the first category. The other techniques belong to the second category. In this video, we will show the first technique, Boolean Difference. For a Boolean function f of a, b, c, we can decompose it into two cofactors. When we fix input a to 1, we obtain the positive cofactor of f with respect to a. It can be denoted as f sub a equal to 1. When we fix input a to 0, we obtain the negative cofactor of f with respect to a. It can be denoted as f sub a equal to 0. As early as 1948, Dr. Shannon proposed the famous Shannon expansion. A function f can be written as expansion with respect to input a, which is a times the positive cofactor plus a prime times the negative cofactor. We can use a mux to illustrate this concept. When a is equal to 0, we will select the negative cofactor. When a is equal to 1, we select the positive cofactor. So after this decomposition, the output of this mux is still the same function f. Now, let's consider the motivating problem. Please perform Shannon's expansion for output k with respect to input b. Now please pause your video and try to solve this quiz. Have you got it? When b is equal to 0, this output is c, so we have ac plus c prime, and we have a complement, so the output will be a prime c. This is the negative cofactor. Now we fix input b to 1, so this signal will be 1. So this is a, this is 0, output will be a prime. So according to Shannon expansion, we will get a prime b prime c plus a prime b. Now we will introduce the concept of Boolean difference. To detect input a stuck at 0,4, the good output f and the faulty output, which is f sub a equal to 0, they should be different. So we can write the Boolean equation as f inclusive or the negative cofactor equals to 1. Now we can do a Shannon expansion of f. So we obtain this equation. And we can expand this expression as a times this term, the negative cofactor inclusive or the positive cofactor, plus a prime times this term, which is the negative cofactor inclusive or the negative cofactor. This term should be 0 because they are identical. Now we can have a simpler expression, which is A parenthesis the positive cofactor inclusive or the negative cofactor, which is equal to 1. This is the condition to detect input A stuck at 04. On the contrary, if we want to detect A stuck at 14, we can write this equation: F inclusive or the positive cofactor equals to 1. After Shannon expansion, we can rewrite it in this way, and similarly, we will get a function A prime times the positive cofactor inclusive the negative cofactor equal to 1. If we compare these two equations, we would observe that the center of this equation are identical. So we can define a useful term, Boolean difference of f with respect to input A is df over dA equal to the negative cofactor inclusive or the positive cofactor. Although the appearance of Boolean difference df over dA looks very similar to traditional algebra, it has nothing to do with derivative. The meaning of Boolean difference being 1 is that f sub A equal to 0 and f sub A equal to 1 are different. That means input A is sensitized to output F. For example, for a 2-input AND gate, where F is equal to AB, if we take the Boolean difference df over dA, we will get the positive cofactor, which is B, and the negative cofactor, which is 0. So the answer is B. When the sign input B is equal to 1, A is sensitized to the output. For an OR gate example, function f is equal to A plus B. If we take the Boolean difference of f with respect to input A, we will get B inclusive or 1, which is B prime. When the sign input B is equal to 0, A is sensitized to output. So now we know that the meaning of Boolean difference is that f sub A equal to 0 and f sub A equal to 1 are different. That means A is sensitized to the output F. So if we want to find all the test patterns to detect input A stuck at 04, we should have A times df dA equal to 1. The former term, A equal to 1, means fault activation. The second term, Boolean difference equal to 1, means sensitization or fault effect propagation. Consider the following circuit with output F. To detect input A stuck at 04, we will need to apply test pattern A equal to 1, and we want to sensitize this fault effect to the output, so df over dA is 1. Similarly, if we want to find all the test patterns to detect A stuck at 14, we would need to satisfy this condition where A prime times df dA equal to 1. Here is an example. Consider this circuit. If we want to detect input C stuck at 04, what would the test pattern be? First, we find the Boolean expression for the output f equal to a plus b parenthesis c plus c prime d. The set of all tests for c stuck at 04 is c times df dc equal to 1, where df dc can be found by this formula. So c times df dc is equal to acd prime plus bcd prime plus a prime b prime cd. This term must be 1. So we can find all the test set. It can be 1x10, where x represents don't care. This corresponds to the first product term. x110 corresponds to the second product term, and the 0011 is the third product term. If we need only one fully specified test pattern, we can use, for example, 1110. If we want a partially specified test cube, we can use 1x10. Let's verify our results. Suppose we apply the test cube 1x10. Then we will get 1 0 here and 0 1 here, and we can propagate it all the way to the output, so we can detect the fault.
Okay, now it's time for you to work on a small quiz. Given this circuit, we already know that K is equal to this Boolean equation. Question number 1. Please find the Boolean difference, dk over dA. Question number 2. Please use Boolean difference to find all test patterns to detect A stuck at 14. Please now pause the video and work on this quiz. Okay, are you ready for the answer? The answer is like this. When A is equal to 0, K is equal to B prime C plus B. When A is equal to 1, K is simply a constant 0. So we take these two terms and exclude them. The answer is B plus C. If we want to find all the test patterns to detect A stuck at 14, then we take the Boolean difference of dk over dA times A prime. So we will get this equation. So we find 01x or 0x1, they can detect A stuck at 14. We can simply do a check here. Suppose we apply 01x. Output here would be 1, and this is 0, this is 0, and 40 here is 1. So the good output is 1, and the 40 output is 0. In this way, we can detect A stuck at 14. Have you got it correctly?
Now, we know how to detect faults at the primary input. By applying the same technique, we can also detect faults at internal nodes. Suppose G is an internal signal of the Boolean function f, as shown in this figure. The function f can be written as function w of G and the other primary inputs y. If we want to detect the stuck at fault at the internal signal G, the conditions are the same. To detect G stuck at 04, we will need G times the Boolean difference dw dg equal to 1. If we want to detect G stuck at 1, 4, we will need G prime times the Boolean difference equal to 1. Here is an example. Suppose we want to detect G stuck at 1, 4 at the internal input. We can decompose this function into two parts, where G is equal to A plus B and F is equal to A plus B parenthesis times C plus C prime D. So W is equal to GC plus C prime D. Function W is defined here. So now, the Boolean difference dW over dG is the negative cofactor with respect to internal signal G and the positive cofactor, which is equal to C. So, to generate a test for G stuck at 0, 4, we will get A plus B parenthesis C. To get the test for G stuck at 1, 4, the answer is A prime B prime C. So now let's verify our test pattern by applying 0, 0, 1x to detect the G stuck at 1, 4. Because A, B's are 0, so we have 0/1 here. And because C is 1, so we can propagate it, and then we propagate the full effect all the way to the output. So we have the correct test pattern. If we can decompose a function into two, then we can use chain rule to find the Boolean difference. Suppose that we can decompose the output f into two functions w and u. If we want to find the Boolean difference of f with respect to input xi, which is one of the primary input, we can decompose this into df dg times dg dxi. So the chain rule can be written as this, which is very similar to the chain rule in traditional algebra. Now let's look at an example. Suppose we decompose this circuit into two functions where G is equal to AB and W is equal to GC plus CD. So we can take the Boolean difference dW over dG, which is CD inclusive or 1 equal to C prime plus D prime. And then we take the Boolean difference dG over dA, which is B. So dF dA is equal to dW dG times dG dA. So that would be C prime plus D prime parenthesis B. Boolean difference sounds like a very nice technique to find the test patterns. However, Boolean expression for every output may not be always available, especially for modern large design where the circuits are synthesized by automatic tool. And the automation for the Boolean difference is pretty difficult. Finally, generating all the test patterns for 4 is actually a waste of time, because we only need one test pattern for each 4. So, for the above reasons, Boolean difference is actually not very useful in practice. Here is a summary of today's lecture. In this video, we introduced the Boolean difference technique, where BD equals to 1 means that the input A is sensitized to the output. The test pattern to detect A stuck at 0,4 can be written as A times df dA equal to 1. For internal signal G, we can find a similar expression. Finally, we introduce the chain rule, which is very similar to that of traditional calculus. At the end of this video, we have two FFT for you to think about. Consider this circuit. We have some input xi shared by both function u and the w. If we want to detect G stuck at 4, can we apply the same equation here? Is there any problem? FFT number 2. This is the same circuit where xi is shared by both function u and w. Can we still apply the chain rule where df over dxi is equal to df over dg times dg over dxi? These are two fun questions. Please enjoy them. Thank you for watching.